This video is on gas pressure. So gases, and we learned about their kinetic molecular theory of being in constant random motion. Gases will exert a pressure on anything. So as gases are moving around, they're going to move until they hit something and then they bounce and will move into a different direction. So this is a very good visual of what I want you to think about when you think about gases. So the particles will go until they hit a wall and then they'll bounce off in constant random motion. As these particles hit the sides of any container or anything that they come in contact with, that is a force. And if we look at the force over a unit of area, that is what we consider to be pressure. So our atmosphere that is surrounding us is full of gases, and those gases are in constant random motion, just like these gas particles are right here. And they're striking you, they're striking me, they're striking the desk, your pencil, all of those, and creating that pressure. So when you hear the word pressure, I want you to think about gas particles banging on the walls of a container, because that's what pressure is. And that's a good visual to have in your head. Now, how we measure pressure is through a barometer, and barometers are of all different types, and they're pretty easy to make. You can make a homemade barometer. Barometers measure atmospheric pressure. The first one was developed by Torricelli, and it is considered unsafe now, but back in the day, we used mercury for a lot of things. So we have this open dish of mercury, and inserted into it, we have basically an upside down test tube. Now, we've taken all the air out of this test tube and put it here into this dish of mercury, and the open end is down here, and this top end is closed. Well, the gases that are all around us in the atmosphere are hitting everything, and including this dish of mercury. And so the particles would be hitting the mercury surface, and that's going to cause the mercury to rise up into this tube. And they measured how high it made the mercury rise. And consistently, it was right around 760 millimeters. Sometimes less, sometimes a little more, but usually right around 760 millimeters. So that became one of our first units of pressure. We measured it in millimeters of mercury. And our standard atmosphere is 760 millimeters of mercury. That's just on standard about how much pressure it exerts. Now, here in America, we are going to use our empirical units to express pressure. So it's usually measured in pounds per square inch, or PSI. And you might notice that like with car tires, and it has PSI written along the side. Our standard atmosphere that I was talking about is 14.7 pounds per square inch. So that means every square inch on your body has the atmosphere is hitting it with a force of 14.7 pounds. That's a good sized cat. That's a lot of pressure. We don't necessarily realize that because it's all we've ever known. And this pressure is pretty constant. Now, this pressure is also, we do have pressure on the inside of our body. So it is kind of counteracting the pressure on the outside of our body. We're going to look at here in just a minute what happens when you don't have pressure on the inside and you only are exposed to the pressure on the outside of the atmosphere of 14.7 pounds per square inch. Now, in science, because we communicate with people in lots of different places, we tend to not use the empirical units, and so we use other units. Now, we kind of went a little crazy with the units of pressure. Here are just a few that we're going to use in this class, but there are a whole lot more. So, one atmosphere is our standard atmosphere, and so atmosphere is a unit of pressure. Well, our standard atmosphere, if we go back to that barometer, was 760 millimeters of mercury. That's how high it made the mercury rise. So here's another unit of pressure. Well, since Torricelli discovered or created the first barometer, they gave him his own unit of pressure, which is equal to a millimeter of mercury, since that's what he measured it in. So we have another unit of pressure. And then the SI unit of pressure is a Pascal, and that's based on the metric system. So that's what most of the world uses. Now, a Pascal is kind of small, so a lot of times we just use a kilopascal. And so our standard atmosphere, if we measure that 14.7 pounds per square inch, 700 millimeters of mercury, 1 atmosphere, that is equal to 101.3 kilopascals. Now, these right here are given to you on the front of your reference tables, and we can use them as conversion factors. If we are measuring things in millimeters of mercury and we need to convert it to pascals, we can use these two values as conversion factors. Or if I have millimeters of mercury and want to convert to atmospheres, I can use these two. So I'm going to show you how those conversions work. There we go. And let's say I have 740 millimeters of mercury. We had a low pressure system coming through. And I want to know how many atmospheres. Let me write the actual problem down. 740 millimeters of mercury equals how many atmospheres. All right. So what I'm going to do is I am going to pick any two of these. And the two that I want to use is the one involving millimeters of mercury and the one involving atmospheres. So those are the two I'm going to use in my dimensional analysis. Millimeters of mercury are here, so millimeters of mercury have to go here. And my conversion factor says that there are 760 millimeters of mercury in 1 atmosphere. Millimeters of mercury cancel out. And everything on top multiplied together divided by everything on the bottom multiplied together. So I get 0.97. You want to be careful and make sure that you maintain the same number of sig figs. So I had 2 here, and I'm going to need 2 here, and that would be my answer. Now, if I was going to do something else, let's say I wanted, I had my, had 740 millimeters of mercury, and I wanted to know how many kilopascals that was. I'm going to use a different set in my conversion factor. So I'll start still with the number they give me in the problem. And this time, the two conversion factors I need are millimeters of mercury and kilopascals. So I need this one and this one. They're all equal to each other. So again, you can pick any two that you want. Millimeters of mercury are here, so they need to go down here. And my conversion factor says there are 760 millimeters of mercury in 101.3 kilopascals, because that's what I want my answer in. So 740 times 101.3 divided by 760. And I end up with 99 kilopascals. So again, you can use any two of these, and they are given to you on your reference table for your conversions in pressure. All right, so I have some practice here. Go ahead and pause this video, work these out, and then I'll go over the answers. Okay. So hopefully you were successful in all of these. So the first one that we're going to look at is that 500 millimeters of mercury and going to atmospheres. So that's very similar to the practice problem I did. We're going to use these two as my conversion factor. And so 760 millimeters of mercury have to go on the bottom and atmospheres on top. Number 2. We're going to use these two as our conversion factor because we want to go from kilopascals to atmospheres. So kilopascals has to go on the bottom and atmospheres has to go on the top. The next one looks like this. So the two conversion factors are atmospheres to millimeters of mercury. So atmospheres are here. So atmospheres have to go on the bottom, and 760 millimeters of mercury has to go on top. And that's my pressure. And then the last one, I'm going from kilopascals to torr. So this is my conversion factor. And I've got kilopascals, so that has to go on the bottom, and torr has to go on the top. And then that is the correct answer there. So those are pressure conversions. All right. Like I said, pressure, the atmosphere exerts an extraordinary amount of pressure all the time because there's a lot of gas molecules surrounding all of us. And that 14.7 pounds per square inch is a pretty powerful punch. All right, so here I have a little video that has a can. This is an open can, and I'll just go ahead and let's play this here. So this is a can, and what we're doing is we're going to take all of the air out of the inside, and we are going to only exert it to the pressure from the atmosphere. So this can is open. It stays up like this and isn't crushed like what you just saw because it has pressure on the inside. So we have the atmosphere pushing on it from the outside. We have air on the inside pushing out from the inside. And so it stays upright. But what happens, what we're going to do to try and get all the air out of the inside is we're going to we're going to put a little bit of water in that empty can, and we're going to heat that water up. We're going to heat that water up, and here's some little water molecules here. We're going to heat those water molecules up, and they're going to start moving around, and then we're going to get them so hot that it creates steam. That steam is going to expand to fill the can and get all the air out of the can. Then we're going to turn the can over into a cold beaker of water. It's cold, so it's going to make that steam go back to that tiny amount of water, pretty much leaving the can empty. So there's the water expanding. It's going to push all the air out. And so now we have a can full of steam, cold water, and then that water condenses so that it is the water does condense into a very small amount, leaving the can completely empty on the inside. And so all that's going to act on this can is the pressure from the outside. So here, that is what 14.7 pounds per square inch will do to you if you didn't have any pressure on the inside. I have a couple of others that I can show you. Let's see, this one, we can do this to a 55-gallon drum. So heating it up, they've got a little bit of water into the drum, and they're going to create steam, which pushes out all the air. They seal it up, and then they're going to put it in a kiddie pool with some ice water. And the steam condenses, and then the atmosphere is going to act on that 55-gallon drum, and boom. The 14.7 pounds of pressure that's only on the outside crushes this like that aluminum can, except this is a 55-gallon drum. All right. So let's see. I have another one that's pretty impressive. This one is Germans. They actually have, they did this to a train tanker. So they did the exact same thing. They put water in it, heated it up, got it full of steam, and then they sprayed it with cold water. And that's 14.7 pounds of pressure of the atmosphere acting on a tanker. Here, they're going to show it to you again because it's pretty impressive. All right, so that is the power of that atmosphere. All right. I don't know what that is. Okay, So standard conditions for gases. Our standard atmosphere is 1 atm, which is 760 millimeters of mercury, which is 101.3 kilopascals. This right here is a screenshot of what is actually on your reference tables. So your standard conditions are there. So you need to make sure that you know them, or at least know where to look for them. So standard pressure is 1 atmosphere or its equivalent, and that's also where you're going to find these conversion factors. Standard temperature, gases like it cold. So that's 0 degrees C, although usually we probably want to go ahead and memorize it as 273 Kelvin, because when we deal with gases, we have to look at them under the Kelvin temperature scale. And that is standard conditions for gases, also referred to as STP. So you need to make sure that you know those conditions or know where to find them, because later on we're going to have math that you will need to solve math problems, and it may just say a gas under standard conditions, and you're like, I don't have enough information. Oh yeah, if it says standard conditions for a gas, they're telling you what the pressure is and what the temperature is. Okay. Now let's talk about vapor pressure of a liquid. Pressure, again, those gas particles banging on the walls of a container. This one is the pressure of a vapor above a liquid in a closed system. So if I have a closed system or closed container, like a water bottle, that's my favorite example for vapor pressure. Some of the liquid particles are going to vaporize. We know water evaporates, and you know this if you ever left a water bottle in your car overnight, you're going to come back and it's going to have some condensation on the top. That means that things did evaporate. So evaporation only happens at the surface, and it is going to gain enough energy to escape its attractive forces. Those particles then bang on the walls of the container, and they create that vapor pressure. Now, as they hit the walls of the container, they're going to kind of lose some energy, and they'll kind of succumb to their attractive forces again, and they'll go back into a liquid. But others will then evaporate, and eventually you end up with like a little cycle, which we call in chemistry equilibrium. All right, so here's a nice visual particle visualization of what I was just talking about. So I've got my closed container, so I've got a stopper in here. I've got some water, and some of the particles at the surface will evaporate. Evaporation only happens at the surface. So they gain enough energy to escape their attractive forces. And then they're going to come out here and they're going to hit the walls of the container, creating pressure. They lose energy and they'll go back into solution, but others will come out of solution and create a pressure. Given long enough, this will set up this nice little cycle to where every time a water molecule condenses back into the liquid, another one will evaporate. And so we end up with a constant amount of pressure, although it's not the same particles that are causing that pressure, but it's the same number of particles. Now, energy and boiling. That vapor pressure is really important part of how we define boiling. If I were to ask you what is a boiling point? You would probably say the temperature when the bubbles happen, which is an okay answer. I think it's very enlightening, though, to look at the legal schmiegel definition for a boiling point. It is the temperature at which the equilibrium vapor pressure of a liquid equals the atmospheric pressure. So pressure greatly affects the boiling point. And really what we, when we're talking about pressure, it can change our boiling point a whole lot. Now, when we normally talk about, let's say the boiling point of water, we are talking about the normal boiling point of water, which is measured at standard pressure, because that's really how we live our lives. We live our lives under standard pressure. We're about at 1 atmosphere about all the time. It fluctuates a little bit, but not a whole lot. And so for us, pressure is a constant. And so we just think about it in terms of temperature. We're like, it's 100 degrees C. That's when water boils. But that's only at standard pressure. If I increase the pressure, then my boiling point is going to increase because it takes a little bit longer to get to that equilibrium vapor pressure equaling that atmospheric pressure. So that's why people own Instapots or pressure cookers. It's because we can get things to boil at a higher temperature by increasing the pressure. We can decrease the pressure and our boiling point goes down. And so water would boil at a much lower temperature if I decrease the pressure. So pressure and boiling point are very closely tied. In our next, we'll just go ahead and do that. So energy and boiling, you can boil water without actually adding heat. So this is a nice little video here. He's got nice quiet equipment, and he has a beaker of water and it's hooked up to a pump. And so he turns on the pump and it happens very, very quickly. But as the pump decreases the pressure, you're going to start to see this water boil. Now, this water is sitting on a countertop. There it goes. And that's because the pressure is so low above it that it just starts to boil. You could pour that boiling water over your hand and it would feel like tap water. Temperature was not a factor there. Pressure played a really big role in that one.